So now we consider the cross field. The cross field means we have the uniform E field and also the uniform B field. Don't ask how to generate the uniform B field yet. We'll let you know in the next chapter, but now we assume we have the uniform E field and also the uniform B field, and they are perpendicular to each other, as you can see in the graph. Here we have two plates. Of course, these two plates can generate the uniform E field because it's like the capacitor. So this is, for this region, we have uniform E field pointing downward. And we also assume that we have the uniform B field pointing into the page. Just now I mentioned the cross means the pointing into the page. So this is called a cross field. They are perpendicular to each other. And now here, this is a circuit. This is a circuit to generate some charge. So this is a battery, and then there will be some charge shooting from here and over this hole. So that we can guarantee the charge is moving horizontally. If it is not horizontally, it will block by this. It will block here. So as long as it is moving horizontally, then it can go through this hole and then shoot to here. Okay, so this is the fundamental setting. This is called the vacuum pump. So if a charged particle moves through a region containing both electric field and magnetic field, it can be affected by both electric force and magnetic force. When two fields are perpendicular to each other, they are said to be cross field. If the force are in opposite direction, one particular speed will result in no deflection of the particles. So this means that suppose the charge is negative, for example, is an electron, then this charge will have a velocity v pointing to the right side, and this is a negative charge, minus q. So as long as it is a minus q, then the electric force acting on this charge will be pointing upward. So Fe is pointing upward, right? And V is pointing to the right, B pointing to the bottom. So V cross B, pointing into the page. B is pointing into the page. So in this case, V cross B. So your hand point to the right side and cross to into the page. So V cross B also pointing upward. But here we assume the Q pointing Q is a negative. So in this case FB is pointing downward. So Fe equals QE, and this is Q times V cross B. So V is an arbitrary value, and it depends on what is the kinetic energy at this point. And of course we can, of course this velocity can be controlled by these two battery here. Which means that if we can control the ratio between E field and B field, then at a specific point, these two forces will actually be the same and pointing opposite direction, and they will cancel each other. So in that case, this charged particle will go strictly to this screen. Otherwise, if you slightly change the B field, the magnitude of the B field, then they may bend. If FB is larger, then it may go like this. If FB is larger. If FE is larger, then it will go like this. If FE will go like this. Actually, it is not bent there. It will be bent like there. If FB is larger, and in that case, FE is larger. FE is larger. And yeah, so there will be a specific case that FB equals FE, and then the charge will go in a straight line. And of course, in this case, FE equals FB, which means E equals VB. Any questions? So next we talk about a very interesting experiment called the Hall effect. Hall effect. So as we just discussed, a beam electron in a vacuum can be deflected by a magnetic field, and can the drifting conduction electron in a copper wire also be deflected by a magnetic field? So suppose if there are no magnetic field, if there are some current, which means that the charge distribution will be uniform. Charge distribution will be uniform. Now we consider if we have a wire. Maybe I just tell the story first. So in 1879, this guy Hall, a 24-year-old graduate student at Johns Hopkins University, showed that they can. So this Hall effect allows us to find whether the charge carrier in the conductor are positively or negatively charged. Beyond that, we can measure the number of such carrier per unit volume of the conductor. So actually, this experiment really find that there should be negative charge, which is really moving in the conductor. So now this is the setting. We have a wire. This part is the wire, and then we assume the current is going from top to bottom, going downward. And now we assume the charge is negative. Which means that the charge should be moving upward. And in that case, we also have a uniform B field pointing into the page. The B field is into the page. So V cross B is pointing to the left side, and V cross B pointing to the left side. Using the right hand rule, you can simply determine the direction. And Q is negative, so FB point to the right side. In this case, there will be a force acting on this charge, which means that there will be more and more negative charge accumulate on the right side. Which is shown here. So you can see the negative charge accumulate on the right side. However, this should be electrically neutral because it doesn't have excess charge. More charge go to the right side, which means that on the left side there will be positive charge, and it is electrically neutral because the charge keeps moving forward, but it tends to go that way. And in this case, this positive charge and negative charge distribution will generate a E field inside the conductor. The E field is induced by charges. Induced by charges. So there will be an E field pointing to the right side, and now we can see that this is negative charge. The E field point to the right side, so there will be a force Fe point to the left side. So Fb point to the right side, Fe point to the left side. So at the very beginning, there are no charge accumulated on the right side, so Fe is small, so that there are more and more charge will go to the right side. In this case, the E field will become larger and larger, so that this force, this Fe will become larger and larger, so that at some point that Fe and Fb will be the same in magnitude. Then there will, the force, the charge will not further accumulate on the right side, because this force is cancel each other. So all the charge will keep moving upward. So this is what we call the Hall effect. The Hall effect. So actually, this tells you what I just told you just now. Electron move to the right and piling up on the right edge of the chip, leaving uncompensated positive charge in the fixed position at the left edge. So when a uniform magnetic field B is applied to the conducting strip carrying current I, the field perpendicular to the direction of the field, the Hall effect potential difference. So in this case, we will call this, you can actually measure the potential difference between these 2 points, which is called the Hall effect potential difference. Hall effect potential difference, because there are more negative charge on the right side, more positive charge on the right side. So there is a potential difference between the left edge and the right edge. So in this case, suppose the width of this wire is D. So we can have V equals ED. We assume the E field is uniform, and this one is from Fe equals Fb. And actually, they have the opposite direction. So, So and all the vectors are perpendicular. So we just ignore all the cosine theta, cosine sine phi like that. So in this case, we have QE, which is the electrostatic force, and QVDB is the Lorentz force. So QE equals VDB, and Q can be cancelled, so that we have E equals VD times B. VD is the velocity. And in the previous chapter, we also know that VD is J over NE, which is I over NEA. A is the cross-section area. So we can we can just plug in VD into here, and then we plug in E equals V over D here, so that we have Q times V over D. Q times V over D equals actually Q can already be cancelled, so that we have V over D equals VD, which is I NEA, and then times B, something like this. So this is actually E, this is VD. So in this case, you just move n to the left side and v over d to the right side, so that you have v. First, you have bi on the top, and then a over d. A is the cross-section area, and then divided by d will become the L. So L is A over D. L is A over D. A is the cross-section area, and then A over D will become the L, which is the thickness of the strip. And then we also have E and V here, so that we can get 2812, this equation. So actually, this is the density of the charge, of the carrier charge. Can be determined by B. Actually, we can control the magnitude of the magnetic field. I, actually, we can also measure. V, we can also measure with a multimeter. L is, of course, can be measured by a ruler. E is a fixed constant, which is 1.6 times 10 to minus 19 coulomb. So actually, we can calculate the charge density due to this setting, due to the Hall effect experiment. And we can also determine that V is VBD, because here we have E equals VB. Actually, V is VD, but here I only write V here, and E equals V over D. E equals V over D from this equation, so that we have V over D equals VB. So we just move D to the left side. So we have V equals small v times BD, which means that this potential difference between the left edge and the right edge will be the multiplies these three numbers. The multiplication of these three numbers, V times B times small d, related to the width and the magnetic field, and also the velocity. So this is called the Hall effect. And one point I have not mentioned is that if, because just now I mentioned that it tells you whether it is positive or negative charge, but at the very beginning we already assume it is a negative charge. How do this statement to be correct? So now we assume it is a positive charge. The direction of I is the same. In this case, VD pointing downward. The B field still pointing into the page. So V cross B will be point to the right side. And Q is positive. So FB also point to the right side. But actually, we can really measure that the potential difference, or the electric potential, is that this side is higher, this side is lower, V is larger. This side V is smaller or lower. However, if it is a positive charge, this charge will go to the right side. It should be the other way around. In this case, it is not possible that the moving charge to be positive charge. or majority of the moving charge cannot be the positive charge. It must be negative charge for the majority of the moving charge. Any questions according to the referring to the Hall effect? So next, let's consider a sample problem. So here we have a solid metal cube of edge length d. So this is a cube DDD for the three sides. So d is 1.5 centimeter and moving in the positive y-axis. And at a constant velocity of a magnitude 4 meters per second, the cube moves through a uniform magnetic field in z direction. Okay, so which cube face at lower electric potential, which is at higher electric potential because of the motion through the field? Okay, so now we need to consider the Hall effect for this cube. Now we assume there is a B field pointing to the Z direction, and then this cube moving upward. So now in this case, we will consider the charge. The charge should be negative charge. And as long as we move this cube upward, then of course the velocity is also pointing upward. And B is pointing to the Z direction. So V cross B pointing to the positive X direction. V cross B pointing to the right side. And this is a negative charge, so FB point to the left side. So in this case, for this cube, the negative charge will accumulate on the left surface. This is negative. And for that size, for this size, it will be like positive. Which means that the right side, the right surface is at a higher potential. Any questions? Okay, so next, what is the potential difference between the phase of higher and lower electric potential? So we already know that this side is positive charge and the other side is negative charge. So to determine it, to determine the potential difference between them is very easy, because it is just use this equation capital V equals small v times b times d. So v is this velocity, 4 meters per second, and then b is 0.05, and then small d is 1.5 centimeter, which is 0.015. So this is a 3 millivolt. Not a large voltage, but it can be measured. It is measurable. Okay. Yeah. Any questions? No question. So next we talk about the other effect. It's called the circulating charge particle. So actually we also have a cross field here. We assume we have the cross field. So a beam of electron is projected into a chamber by an electron gun. G, the electron enter the plane with a speed v and then moving in a region of uniform magnetic field directly out of the plane. So as a result, the force, magnetic force will act on the we don't have cross field here. We don't have cross field here. We only have a magnetic field here. So as long as we project the electrons perpendicular to the magnetic field, then the electrons will follow a circular path. Which is actually like a circular, so like a circle. Also is not really like a circle. Maybe it should be larger, because it feels like it should be. Maybe this one is the. I'm not sure. Maybe this graph is not very good. I'm not sure. If it is, this one is the radius, it should be larger. But yeah. Anyway, it should be like a circular path. So so this is actually the force, the Lorentz force, which is QVB. We assume V and B are perpendicular to each other. So this is actually the force. The force equals ma, which is the Newton's second law of motion. And for circular motion, you should have learned that A is V squared over R. A is V squared over R. So in that case, we have this expression, QVB equals mv squared over R. So V and one of the V can be cancelled. So we know that the radius of this circle should be like R equals mv over QB. This is the radius of the circle. Because you can imagine the B field pointing into the page for this case, or out of the page. The B field should be out of the page. Yeah, the B field should be out of the page. In this case, V cross B point to that side. V cross B point to this side. And this is a negative charge, so FB point to this way. So as long as V is going upward and the force pointing to the center of the circle. So this, the charge will turn a little bit to the left. And in this case, we point to this side, and then the force will also point to the radius. So it will become a circular motion. Circular motion. I suppose you should have learned it in high school for the circular motion. So now this sample problem is a bit more complicated. So it is so the charge entered the cross field actually. So an electron with a kinetic energy of 22.5 eV moved into a region of uniform magnetic field of still not cross field, but it entered not perpendicular to the B field. The B field is pointing upward. We point to this angle for this part. V perpendicular is perpendicular to B, but this component parallel to the B field. So in this case, this V cross the B will be 0 because they are parallel to each other. Only this part will contribute to the Lorentz force. Only this V perpendicular will contribute to the Lorentz force. So we need to separate them, and which means that in this maybe we call it the XY plane. This is the XY plane, and then this is the Z direction. So in the XY plane, it will have the circular motion, but in the Z axis, it will move in a uniform speed. So when you add them together, it's just like a helix line. 螺旋线. So it is like a helical path taken by the electron. So an electron with a kinetic energy 22.5 eV moving into a region of uniform magnetic field, it should be field, not field, of the magnitude 4.55 times 10 to minus 4 Tesla. So the angle between the direction of the B field and the velocity is 65.5 degrees. So what is the pitch? Pitch means the vertical direction between the helix line. This is called the pitch. Denote it as small p. So what is the pitch of the helix path taken by the electron? So last semester in the midterm exam, some students still ask, "Oh, what is the pitch?" And I said, "Oh, there already a sample problem there." So now we first determine the velocity first because we get the kinetic energy of the particle. So V equals square root of 2k over m. So this is 22.5 times 1.6 times 10 to minus 19. Similarly, we need to convert it to joule, and then m is 9.11 times 10 to minus 31, which is the mass of an electron. And so this is 2.81 times 10 to the 6th power meter per second, the velocity of the electron. Okay, so next we need to determine the pitch. So first we should have the V parallel. V parallel is V cosine phi, which is 2.81 times 10 to the 6th power cosine 65.5 degree. So this is the velocity of these parts, and the pitch should be V parallel times the period. it takes to finish a circular motion. It should be like V parallel times 2 pi m over QB. So this is the period of the circular motion. So in this case, we can substitute all the number 2.81 times 10 to the 6th power cosine 65.5 degree. And then 2 pi times the mass is 9.11 times 10 to minus 31. And then Q is 1.6 times 10 to minus 19 times B is this one, 4.55 times 10 to minus 4. So it would be 9.16 centimeter. Of course, you can also determine the radius using this equation. Determine the radius. By R equals mv over qb. And of course, this t is something like 2 pi r. 2 pi r is the length of a circle, and over v will be the period. So we can come up with this expression: 2 pi r will be 2 pi mv over qb, and then over v we just cancel v. So we have 2 pi m over qb here. So which is the period of the circular motion. Any questions? Okay, if no question, let's stop here and we have quiz tomorrow.